Hi everybody, Dario Fresu here from fresuelectronics.com, and today we are going to review this MPPT project for solar panel applications, and we're going to review it in terms of EMC and also signal integrity. So the first thing that you are going to look is the stack up of the board. So this is the most important things once we are doing the projects, and it's super important for us because this will tell us 90% of the performance in terms of EMC. So let's jump straight into that. So as a first thing, what I want to check is that all the all the layers are enabled, so that like this I can see which are the signal layers and also the plane layers. But also I will check it right from the layer stack manager here. So I go to the layer stack manager and I check what's the stack up of the board. So at this point I didn't even check the schematics yet, but I just want to have an idea of what it is this project about and how it has been implemented. So we can see that the stack up is two-layer stack up. So we have signal on the top and signal on the bottom. So I already know that for these type of applications, we're going to have some troubles here. And this is because we don't have a return reference plane for the signals. So what do we mean by reference plane? So the return reference plane is this one here. So it's the return reference plane adjacent to the signal traces. So this is important because you're giving in here the reference for the voltage of the signal. So this serves also to contain the fields. If we don't have this one here, then the problem with that is that we have the fields which are spreading around. So in this case, there is no return reference plane underneath, and then the fields start to spread around. But also the other problem is that when we have two signals layers, so we have signal on the top and signal on the bottom, like in this case, you can see here. Then what is the problem? The problem is that the fields are contaminating each other, to say that in simple terms. So the fields on the top signal trace are contaminating the fields on the bottom trace. And this is a problem because then it means that when I have a signal on the top, the signal can be seen from the signal trace on the bottom, and vice versa. So when I have signals on the bottom trace, then I'm going to see the signal also on the top layer. And this is what is called the crosstalk. So the signal are seen from both traces, and this is a problem because if you think that this is, for example, this is a reset line, and this signal instead is an interrupt. So maybe you want to measure when the temperature rises at certain levels, and this interrupt signal here on the bottom trace is doing exactly that. But also then you have here the reset line. So this reset your microcontroller or your CPU, whatever you have. So what happens that when you have the interrupt, for example, you have 37 degrees Celsius outside and you need to take certain actions. So this signal is meant to interrupt the CPU so that the CPU can take other measures, so can do other actions. But then what happens is that the signal on the top, which is the reset line, is seeing also the high level of the signal on the bottom, and it thinks that you are requesting for a reset. And then what happens is instead of taking action because you have an interrupt signal, then you're resetting the CPU because the CPU thinks that you're also asking for a reset. And this can be a really catastrophic failure depending on the system that you have or depending on the things that you want to take action for with this signal. Okay, so we don't want to have crosstalk. We want that this signal is contained within this signal traces, and also that this signals is not contaminating the other signal traces. So what we're going to do here is then we have to make sure that we have this scenario so that the field are contained, so that we have a return reference plane which is containing the field. So if you see the electric field lines, in this case from the top they are a little bit going out of the board. So think of this the dielectric of the board. So this is like this dielectric here, so between the two layers. But what happens is that the electric fields are then referencing these return reference planes, and they are contained there. So to do that, what we do is we just use some 4 layers board. So that's why having a 2-layer board is quite hard to do, because If you have a 2-layer board, then what you want to use is a signal on the top and then return reference layer on the bottom. Or the same is you have signal on the bottom and then return reference plane on the top. But using 2 signal layers, then is going to be a huge problem, especially for this case here, because you have a signal on the bottom, signal on the top, and then both fields are just messing with each other. Okay, so we know that we have to increase the layers. We are going to have in here, it says power, but I don't want to have power in there. And I explained that in other videos, why we don't want to have power in that, or in most cases, you don't want to have power in that. And we're going to put another GND. So we are calling GND, but really the best is if you start calling in return reference plane, because at least you don't forget. So here we can call it RRP for return reference plane, and here the same. So at least we know that this is for the return reference plane of the top layer. So before we proceed, then I need to change this one into a signal layer, and so as well also the other one. So this is going to be, I'm going to rename them like that, layer 2, and then I'm going to rename also this one, layer 3, and then here I'm going to have layer 1, and I'm going to have in here layer 4. So here I'm going to put signal, and here I'm going to put signals as well. Okay, now I can save, and I can go back here, and then we can add, for this layer, we can add already some copper plane. This is the return reference plane in the second layer. I'm going to adjust it a little bit. And then I'm going to do the same for the layer 3. So I'm going to place another return copper plane here. Now I'm doing this roughly like that, so the edges are not well done, but it's just to give you the idea of what I want to achieve by doing that. So then I change the net. In here I go and I place the ground, what is called the ground, but call it return reference plane, because then you know what is this for. And I'm going to do the same there. Let's check. Okay. So like this, now I have signals on the top, return reference plane on the bottom. Then I have signal on the bottom layer, and then return reference plane on the third layer. So each signal layer has its own return reference plane. Now let's check a little bit. Now at this point, since we didn't have the return reference plane, so the ground net is ground IR2110. Since I didn't have this as a return reference plane, for sure I had it as a traces. So now I want to check these traces like this copper plane here, and I can get rid of them. I can get rid of them because I have now the return reference plane on the bottom of the signal, so adjacent to the signals. Why this is important? Because if you saw before, in here we had only 2 layers, and between these 2 layers there was a huge distance. Maybe I can show you if I go back. So you can see that here I had before signal on the top, signal on the bottom, but the distance here is 1.5 millimeters. So this is a huge distance. What I did later though was to have 4 layers with a small distance between the 2. So you see that now we went from 1.5 millimeter to 0.3 millimeters, less than 0.3 millimeters. So this is very important because now I have very good coupling between the signal on the top and the return reference plane on the second layer. And the same is between the signal layer on the bottom layer and the third layer here. And by the way, this is also the best way to reduce crosstalk, and the fastest way to reduce crosstalk is to reduce the distance between these 2 layers. So between the signal layer and the return reference plane. Okay, let's go back now. So we said that we want to look for these ground traces because right now they're just taking space. They're not going to be used from the signals as a return reference plane. So we just want to get rid of them. Then the stitching vias here, we're going to get rid of them later on. But so far this is okay. So the other thing that I want to check, this is probably another ground pour. So avoid creating ground pours like this because you can see. So this is a ground pour and it has an antenna-like structure, which means that you have an antenna-like structure like this where you have a dipole. So this is a dipole. You have a signal source and then you have one side here with a certain voltage and one side here with another voltage, with the opposite voltage. So This one is a good radiator, so you don't want to have a structure that form this kind of antenna like structure. So you can see this is the same when you place a cable on one side of the board and another cable on the other side of the board. So this is creating dipole antenna structures, and these are bad because they radiate or they receive also good radiation. So you don't want to do that. So we want to avoid to have this type of structures like this, because if you think about it, this is one side of the dipole and this is another side of the dipole. When a signal here is reaching out, when the signals of this trace, they reach out because they're close to this polygon area, then in here you have a dipole antenna, and this promotes the radiation. So you don't want to have antenna-like structure like this. So better don't use this type of polygon pores. The same here, this is another antenna-like structure. Here is the same, you have this antenna-like structure, because you have to remember that the copper has a certain impedance as well. Between this point and this point, there is a resistance, there is an inductance, and so you're creating a voltage difference between these 2 points, and this is what happens. Then you have a difference in between these 2 points, and then you have a dipole. And you don't want to create these type of structures like that, these type of geometries. So we're gonna get rid of this here, and then you see it starts to get a little bit clean. Then the same we're gonna do with this one there. We're gonna get rid of this, and now you see we start to have some nets that are not connected. But this is okay, we're gonna fix that, and then we're going to get rid of these two, get rid of these two. Now let's enable all the layers. Now I'm going to leave only the signal layers, and I want to hide also the copper plane. So these return reference planes, I'm going to leave them like that. So they are not going to have a splits, cuts, they are not going to have this division. They're going to be full return reference planes. So this is extremely important. And this is important, why? Because I don't want to have impedance discontinuities. Then what we're going to do, so we're going to check now which one are the other three. I have lots of traces here that can get cleaned up, and I can reduce also the inductance of these traces, because what happens is that now I have these pads. Let's take this pad here. So this pad here, before you can see I have a trace which is connected in the 2 pads, but this is adding inductance because the trace in here has a certain inductance, and I want to get rid of that. So you see it has already certain resistance. Altium is calculating already what is the resistance here. So I want to get rid of this, and since I have the return reference plane on the bottom, what I can do is, first of all, I change the grid, then I select the via, and I want to place a via or a via, whatever you want to call it, as close as possible to the pad. And then I'm going to change also the width of the trace. I'm going to use, right now I can use this, I can use the trace which is 0.8, whatever, but this is I need to calculate this width also. I can do that by calculating the width with something like Saturn PCB, where I can calculate the width based on the impedance that I need for power traces, based on the current that I need. So I can use calculators like that, or I can use calculators from whichever website you prefer. Anyways, what I want to do now, I have in here the selection of the layers that I want to connect to that. So I want to connect this ground net, and now maybe just want to, we can do like that, place it in the middle, and then I'm gonna add the via. So what I do with this is I'm shorting the distance, because now I have a very low impedance for this pad to connect it to the return reference plane on the bottom. So what I'm doing is I'm reducing the loop sizes that this net has. Now the same I'm gonna do in the other pads. So I'm going to select all the ground nets, and I can select them with the tab. I'm gonna get rid of them. Same I'm gonna do here, and I'm going to replace all these traces with vias that connect directly to the return reference plane. Same here, I can just select all, then delete, and then I start to clean up all these traces. Same here, I just want to get rid of all these connections. Same here as well, I delete all of those, and then I do the same here. I delete all these connections, so by the end, I'm not gonna have any of this. Okay, So same, there are some other places here, so I'm going to delete all of those. And also I can check when I have some vias that I'm not going to use anymore, because I want to do the same also on the bottom layer. So I can check the bottom layer. See, I have another copper plane with a ground, which we are not going to need anymore. Same here. I can also get rid of all these vias that I don't need anymore. These I can get rid of. This is the same, and this is the same. So you see, just by doing that, I can clean up much faster the layout, and I'm getting rid of things that I really didn't need. So let's do all this cleanup. And by using these traces, really the signals are not going to use this path. They're not any of these paths that are going to be used from the signals, because they will find for sure other return reference planes with better impedance profiles. So with less impedance, and they're going to use this path. So most of the time this can be just parasitics. I'm going to show you what I mean. So they're going to use parasitics, and then they're going to create huge parasitic loops that are going to increase the current loop size, and these are going to increase also the magnetic fields, because if the current loop size increases, then the magnetic fields, then they will increase as well. And this is one of the most common problems that you're going to find when you do EMC test. Okay, so now we clean up this part. Like I said, what I want to do now is to make this connection shorter, so that I make sure that in each part I have very short connections. What I can do is I can place the nets, short net which has very short impedance. I can even make it closer like that. Then I'm going to copy paste. So I'm going to copy, and then I'm going to do the same for the nets. Make some space, and then reduce the distance. And I'm going to do the same job for all the other nets. See that now all these pads, they get connected to the return reference plane, so you don't need to have anymore all these huge traces creating ground loops. Okay, I can do the same here. For all these pads, I'm going to do the same. Now, if you have some pads or so components that require huge amount of current, of course you have to calculate what is the current that I can feed through this via here. So this is a 0.3 millimeters hole size and 0.6 millimeters diameter. So I can do a quick calculation, and I can check how much current I can feed there. So we said 0.3 millimeters, this is 0.6, and then I'm going to leave those as the default. Plating thickness, this is in millimeters here. So this is 1 ounce of copper, and I can see that I can feed through this via 2.16 amps. So if I need to feed more current, then I increase the number of vias, or I increase the size of the via. Okay, you will have to calculate that. Then I keep finishing here. Now when you have like this, you want to keep the same, ideally you want to keep the same width. So I can reduce the width in here. Of course, make it nicer, make the via closer. There you go. The same you can do there. So you can copy and paste here. Then the same you can do there. And you're going to do the same for these other pads. So all the pads that you see that are now unconnected, you can just connect them. You can improve these connections, of course. Same we're going to do there. See, now those are connected to the return reference plane that we place on the bottom. So I'm going to do this, and then I'm going to show you the results. Okay, now that I finished to connect all the ground pads to the return reference plane, so now I can check also what else is going on in here. And of course I did that, but I had a look now also about the circuit in here. So I know what is the circuit about. I know that this is, like I said, an MPPT for solar panel applications. So I know what this is for, what kind of nets to expect, and what I should look for as well. The thing is that I knew already, even without looking at the schematics, that this was going to be a problem for the signals. Especially when I start to see microcontrollers here, because this is a microcontroller. You can see this is an STM32. So I know that the signals rise time, even of a single GPIO in here, can be a problem if I don't have the return reference plane on the bottom. Okay, now the second thing that I want to look for is for things such as crosstalk. And this is very important because I can see straight away, just from the distance between the nets. So if I take a look at these nets in here, I can get close and I can see, okay, these two are not really differential pairs. So if I have any doubt, I can check in the schematics, but I know that SW connection is not a differential pair connection. So I know that these two traces, if I check in here, and if I measure the primitives, look how close they are, the traces between each other. So this is 0.25 millimeters, which is way too close. So this means that the clock signal from these nets in here is going to be seen from this DIO net. One thing that we can do in order to reduce the crosstalk between these two traces is to increase the distance between the traces. So just by using a distance twice or 3 times better the distance, the width of the net. So just using 3 times the width of the trace, I can reduce crosstalk drastically. But also, since we reduce the distance between these two layers, so now I have a signal layer and return reference plane very close to each other, then I know that the crosstalk is going to be minimal. And if I have any doubts, I can always double check. For example, with Saturn PCB, this is a free tool. You can just use this one. But what I can do is use the crosstalk calculator. And then let's suppose that I have in there a 3.3 volts signal on one trace, which is the case for us now. Then I can see what is the couple length. So to check the couple length, I can measure this. So let's put it back together and I can measure. So let's measure the distance from this point through this point. So in here I have 17.5 millimeters. Okay, so I can use this coupled length, 17.5 millimeters. What is the conductor spacing? We saw that it was 0.2. And then look at the conductor height. So this is the height. And right now we have 0.4, 0.6, 0.16. So we have 0.16 and I can check in here and I can place 0.16. So actually I want to show you that. So when we have 0.7 millimeters, we have 3.8 volts coupled in here between these two traces. So this means that if I have 3.3 volts signal in here with a 1 nanosecond rise time, then I can see here 3.8 volts. So if I have a reset line here, and if I have an interrupt line in here, each time I issue an interrupt, then I reset the board. And this is why most of this problem happens. So what I want to do is now check what is the crosstalk now that I have decreased this distance and I'm using 0.26 millimeters. And let's see, it's already half. But still, it's a lot because I have a conductor spacing which is too close to this distance here. They are too close to each other. So what I can do is increase this at least double and look how much it reduces the crosstalk. So I can use it very large. Let's go for 0.8 millimeters. Look, now it's good. Now it's already good. So you have to be careful because some signals get triggered from very low voltages. So some MCU or some CPU, they have very low threshold voltage to detect the high signals. And then if you have already a crosstalk which is high enough, it's going to think that you are issuing a high signal when in fact you don't. And this is going to create these kind of problems. So what we do is we increase the distance between the traces. So now we will increase this distance. And let's measure now if I use this distance here. Let's adjust maybe this one a little bit more. Let's see now what is the distance between the nets. So now I have 1.46 millimeters. So let's check how much it is for 1.46. So I'm not gonna have any problems there. Now remember it was 0.254. We went from huge crosstalk to now almost nothing. There you go. So this is one way to minimize crosstalk. Just increase the distance. So the same we can do for these traces. So I want to use the space that I have in the board and also to reduce the length of the traces. So I reduce the length, I increase the space within them. You see, now first of all, I'm increasing the distance between these coupled length, and I'm also increasing the distance between each other. Same I can do there. I can use this here. And then I'm going to analyze this section that I have a certain distance. And I'm going to replicate the same for the other traces. So use all this distance if you can. And you're going to improve it for crosstalk already a lot. So same we can do here. Then of course you are going to optimize the layout. But first we are going to reduce the crosstalk. And we're going to reduce it by improving the layout a little bit more. Now the same applies to the other layers. So here I can do the same for the bottom layer. So let's go to the bottom layer. And you can see here I have a huge distance. So here there is really no need to have these traces close together if they are not differential pairs, or if they don't need to be close to each other. So if they are not referencing each other, I don't want to have this kind of behavior. So I'm going to increase the distance and also shorten it. So if I can shorten the length of these traces, it's even better. And then increase and increase more. So here I'm going to have much less crosstalk already. Then the same I can do for the others. If I can reduce, so this is going to reduce the length of the trace. And these parts, same here, is very important as well. Check the traces. I know these are not differential pairs, so I increase, use the space, and then of course you're going to improve this. Okay, and the same I'm going to do for the others. This is already going to improve so much the layout. So many problems are going to be reduced or even avoided altogether just because we increase the distance between the traces. Now, of course, these parts, like I said, you're going to improve them. You're going to make them nicer also. You want to have also a nice layout, not just pure performance, but also nice, because your clients are going to see your layout and they're going to judge you based also on the look of it. Same for these traces, increase, reduce distance, reduce length, okay, wherever is possible. Much nicer, okay? Another thing that is very common is to use transitions from one layer to the other layer. So this signal is going from top layer to bottom layer. But the problem in this is that once we do the layer transition, so when we go from top layer to bottom layer, then the problem here is that when I go from here and I go down, then in these parts, then I have the fields that have no more return reference plane or no more reference. So what happens there is that then I have again the case where I have these uncontained fields. So during the transition, I have already the case where the signal is no more contained. Let me show you the right picture. Is no more contained like in this case, and then the fields start to spread around. And these are going to be seen from the instruments when they're doing the electromagnetic compatibility tests. So how do we solve this issue? What we can do, so first of all, let's change views. What we can do is we can change the way we view the port. And we're going to select the color by layer. And like see that also, let's increase the distance. You can see that the signal from the top now has always the reference, because this plane here is the reference for the fields in there. So the fields will be coupling like this, coupling like that. Okay, like in the case that I showed you before, like in this case. Right now the signal will go on the top and then we reference to the bottom for the whole length of the trace. But then it comes to this point, and again in this point now it does not have anymore the reference. So the fields will start to spread around. So the way that we take care of these effects, so the spreading of the field until it reaches the bottom layer, is by adding a return via next to the signal. When we do that, then the signal, actually let me show you. When we do that, we just place the return vias. Better if we can place more, because like this, the fields are better contained, of course. So what happens in this case is that now the signal comes to this point. Signal is coming, here has reference, because this is the reference plane. It comes to this point, and then it comes here, and then it finds the return. So here, it comes here, but now it has the return. So this is the return path, or this via, or the other via that we place around. So for the whole transitioning to the other layer, the signal is going to have a return reference plane. Not a return reference plane, but a return reference via in this case. So the current loop now is very short. It's going to be current loops are going to be very short, like that, until it crosses layers. It goes to the other side, and now the signal is going to find again. So here has the reference to this via and this via, and now when the signal goes to the other signal trace, it will find this light blue colored layer, which is the return reference plane, and it's not going to have any problems. It will keep propagating this way, but still is going to have a good return reference plane, like in this case. So now what you can do is for each signal transition, so wherever we have a transition of layers, we place close by, let's say the return planes, we place close by a return via. So here return via, here return via, also here we place return vias next to the pins, here are return vias, here are return vias. Wherever we transition layers, we want to have a return. Now let's see what else we can improve in this board. So again, like we said, all these nets, they need to be, all these traces, they need to have a little bit more space between each other. But then the next thing we're going to check is this. So in here, these traces close to the edge. Usually you want to have them a bit far from the edge because you don't want the fringe fields, which are the one that we show here. So these are the fringe fields. So fields that can extend outside of the port. You don't want them to spread around. So you want to have the signal trace inside of the port, so more inside as possible, so that the fringe fields, instead of going out like that, they can reference the return plane adjacent to it. Okay, so you want to have this case and not this case, because again, these, when the fields extend outside of the board, they are not contained. This means when you do the EMC test, then they're going to appear in your instrument. So the same we're going to do there. This is way too close to the edge, so let's reduce this. Let's bring it more inside. Let's shorten the length of the trace like this. It should be fine. And then all the way you can improve it, all the way like this. And then you see here we have what is called the stubs. So you don't want to create these sort of branches like that. In here, what happens? It happens that the signal, either coming from this way or from other ways, it doesn't matter which way it's coming from. The signal is coming to this point, and then it sees these two branches. So this is called an impedance discontinuity. Suppose that here you have a 50 ohm impedance. Then you come to this point, and then now the signal will split because it sees impedance here, but also another impedance there. So these two different impedance, they will cause some sort of reflection from the signal, and then they will reflect back and will cause signal integrity issues. So you don't want to create these branches like this. And one of the ways that we're going to fix that is by creating point-to-point connections. So you want to go from pad to pad instead of connecting. For example, here we go here, and then we branch there. No. So what we're going to do is, instead of branching there, we continue the connection from point to point. And then you see, now I don't split anymore, so the signal will come this way. And then instead of branching like before, it just flows on this direction. And it doesn't see any splits, any change of impedance, let's say. The same we're going to do for the other traces. Again, these ones. You can see that these issues are very common. Those are between the top 10 issues. Okay, so we said that we're going to add for each transition of layers, we're going to add at least one return via. This we're going to do it for all the nets, for all the transition vias. Then the other thing that we can check is impedance discontinuities. And I can see already one here. And this is this one there. Why impedance discontinuity? Because, so this trace, this net in here has already a certain impedance. Suppose that this is a 50 ohm impedance. Then the signal comes in here and it sees 50, 50, 50 ohms, 50 ohms, 50 ohms. Then it comes to this point and there is a change of impedance. what happens when we have a change of impedance? We have reflections. When the signal comes here, it sees these impedance discontinuities because in here is 50 ohm, but then here the impedance changes. So this point, the impedance is no longer 50 ohms. And then what happens is when the signal is transitioning between this one, between this top layer and the bottom layer, then it sees the impedance discontinuity and it reflects. And we don't want that. So use the same width, use it constant. So this is 0.254. So I'm going to select this net as well. So what I want to have is 2.4. So now the signal comes to this point. You will see a little bit of discontinuity from the via as well, because there is a change of impedance, unless you design this via with 50 ohm as well impedance, which you can calculate with the Saturn PCB toolkit or with other calculators. But anyways, what's important is that now the signal comes here, sees a little bit maybe of discontinuity from the impedance of the vias, but then it goes back to have 50 ohm. So there is no reflection of the signal. And then it continues happily ever after until it reaches the point that it has to reach. Now here as well, we need to change this and make it the same. Either you make it this width. If this is a power trace, maybe you want to have it thicker. But if this is not a power trace, then you want to have it with a certain controlled impedance, which is typically 50 ohms, and then connects to this pin. Then now we're going to see one of the biggest issues that this board had was on, I think it was on ground bouncing or some similar problem. So it was a problem of ground bounce. And the problem, of course, it was because, first of all, the ground bounce happens because there is an impedance discontinuity in the return path. If two signals are using the same return path, like before there were traces for the ground, the likelihood that each of the signals, for example, was using the same return path, and therefore they were seeing each other's signals, like we said there was in this case, that this signal was seeing the signal from the bottom layer, then of course the ground bounce will happen, because they're going to choose probably the same path of least impedance, and then when this one triggers, then also this signal there sees that this is triggering and at the same time triggers. And this can happen in the signal path or also in the return path. So when this one happens in the return path, this is what is called ground bounce. Okay, now these problems should be solved. We said increase the distance. Then let's take a look at this one. So here we have the biggest component. So if we come here, we know that we have this buck converter. So if we have a buck converter, then what is going to happen is that, so we have this inductor there, which is taking whatever these MOSFETs here are feeding. So here is basically a filter composed from the L and the C. So what happens here is that we want to take good care of this loop. So the loop is created between whatever we feed from this, and what happens is, like we said, we're going to have here we have a switching current. So switching current means that we're going to have magnetic fields which are changing, and then this path is going to create some huge magnetic fields that are going to be seen from other traces, other devices, and especially when you're doing EMC tests, they're going to be picked up from the instruments, and they're going to place you a huge fail on your report. That's what happens. Because the return current loop is so big that the magnetic fields are big. And then they are over the limits and they're going to be detected. So what we want to do at this point is check, first of all, where is the inductor? Now select the inductor here and then the capacitors. So the capacitors, now let's change view. Let's go back to the screen so we can see what's happening. Now we see that we have the inductors there and the capacitors here. What I'm really interested about is also where is this happening, because we have connectors here. So this is the input. So look at this loop, how big. This is the current loop, comes here. And then in here we have the inductor with the filters. So The current loop is basically like that, and then with the capacitors filter and closes the loop. So this loop is massive. So what I want to make sure is that this loop gets as short as possible. And the way I'm going to do that is, first of all, let's check where is this connector there. Okay, so this is not connected, this is just a sign. But what I can check is this fuse, okay? And this fuse is connected somewhere here. I think it's also not placed on the design. Oh, it's here, okay. So we have this, which is the negative, which is basically this sign here. We have this connector there. So we are feeding the buck converter from these two connectors. So this is the plus, this is the minus. Now from there, where do we go to feed this buck converter? So from there we have the fuse. So the signal comes here. Look how large is this loop. Signal comes here, then it goes there, until then it feeds this buck converter, then it comes here, and then what it sees is the capacitors. Maybe you can see it from this point of view. So signal enters here from the cables, whatever it has. You make it a bit nicer. Signal comes here, DC, whatever signal we have, then comes there, comes here, then it comes here, goes to the inductor. So this is the inductor there, comes there, and then it goes to the capacitors, and then it closes the loop here. So this is the current loop. This is the whole current loop. So currents is closing this huge loop. Imagine if you have a huge current loop like this one. What is the changing magnetic field that you have around? It's probably going to be big. Then this is going to be picked up from the instruments during the EMC test, and you're not going to pass the test. So what we want to do is to optimize as much as possible these loops. This loop needs to be optimized. Now, before we only had the copper pores in this area. So we had, if you remember at the beginning of the video, we had this huge copper pore that was connected to the capacitors. So this, of course, has a certain impedance. I don't think it was optimized at all. And it had only two big planes on the top. So it was here, huge plane, huge copper pore, but also it was on the bottom. So huge copper pore on the bottom, and they were stitched together by these vias. If you remember, this was the copper pore, something like this. But now what we did is we connected straight to we have connected already straight the capacitors here, so that now the return current will find better path, because now it's using the whole plane. Let me show you the plane. Now we can take the path of least impedance the way he likes. So instead of being segmented by this huge loop, so before I was probably doing something like that and then finding the way to close. So now we can do something like this, much shorter. Look how much shorter. So now we will do something like that, much shorter signal paths. Okay, these are the benefits of using also the planes. And this happens because we have different return, based on the frequency that we have. So if we have high-speed signal, then the return current will be under the trace. So we have the red trace on the top with the signal forward current. Then we have the return, which is under the signal trace. Because the inductance in this point is much less, so it means that the part of the impedance which is dependent on the frequency is much larger. So we have to take care of this, and we want to create the path of least impedance for the signal to return back to the source. When we have instead low speed signals, then the resistive part is much more important, because this part which is dependent from the frequency is smaller. So you can see that the impedance in here depends much more on the resistive part. So if this is the case, then the signal, in order to return back to the source and close this loop, so you see here you have plus, here you have minus, supposedly, the signal is going to do this, but then it wants to have the shortest path to return back to the source, because this has much less resistance than this path. So then what it will do, the signal is we go here, then there, and then it will take the shortest path and close the loop. But in here instead, it will follow the least inductive path, and then it will close back to the source there. So we know now that this converter, the components between this converter, they need to be placed, first of all, close to each other, but also in a way that minimize this huge loop. So we have to find a way on how to reduce these loops. One of the things that I think we can do is to flip, first of all, these capacitors and place them on the other side, because still, if I change them and I can place them, this polygon, instead of being here, I can place it here, then this is much closer, first of all, but also, since now I'm using the return plane, then the return path will be as well close, because it will not do a huge loop like that, but it will go straight from there. Now, we didn't check even the placement of the components, but of course you want to have some kind of separation between the components. So you want to place the components in, for example, in digital section, analog section, without splitting this plane. So we don't split the planes like some application notes that would recommend. We don't separate the analog section with digital section in the return reference plane. We just separate them by placing them apart from each other. So giving them some distance so that we don't have this coupling that we mentioned before. This is the way we separate them. So we don't cut the planes. We don't have cut the planes or chunks of planes. We don't do that. Or even other chunks like this where we separate this part with this part. We don't do that. We use solid copper planes. Full, no splits, no cuts for both planes. And then you see that this layout will improve 10 times more. So just by applying these simple things that I mentioned here. So I hope that this project review give you some help, and it allows you, first of all, to pass EMC very fast. There are several things that we didn't check yet. For example, the protection for the input and output cables or any connection that you have that goes out of the board. So you want to have some sort of protection there, some TVS diodes, some filtering, some type of protection like this. And this is going to improve, first of all, the immunity of your board to EMI, and also it's going to improve the performance of your board so that it doesn't produce much EMI. Okay, so these are the basic things that we look for, first of all, when we're doing this type of reviews. And you can see it's very simple just by adding 2 more layers, how we can improve so much the layout of the board. Now, for those of you that have bosses that say, okay, I want you to use a 2-layer board instead of a 4-layer board because we want to reduce the cost. Now, you have, first of all, to see if you can really do that. Because if you have, like in this case, you have, let's hide this. So can you do this layout in a 2-layer board? It depends. First of all, can you route all the traces on one side of the board so that you can use the other one as a return reference place? Or when you do the transition of VS, so if you are going to use the transition of VS like in this case, then what you can do is you can use short transitions. So the signal comes here on the top layer, then goes on the bottom layer, and then it comes back from the top layer, and then you can continue on the top layer. So when you make these transitions, they are very short. Of course, you have to place, of course, when you do this transition, you want to place the return vias like we said before. So we're going to, let's assign the different net. So when you do this transition of layers, you want to keep it very short and continue. So come from top layer, keep the same width. So this width should be ideally the same. I think it was 0.24. So you come here, then you go to the bottom layer, then you come up again, place the return vias next to the transitioning via, and then you continue with the signal. And then you can continue on top. So this, you will delete it, and you will have it on the top. Let me make it nicer. So when you see it from this, then you see the connection is very short. So signal comes here, and then it goes on the bottom. It goes on the bottom there, but then it comes up again from this, and then it continues on the top. So when you do that, then the cuts that you're going to have in the bottom layer, if you use it as a return reference plane, they're going to be minimal and they're not going to create many problems. But in this case, I think that we can still route probably this board as a 2-layer board, but we have to figure out how to place all the traces on one side and then use the other layer as a return reference plane. So either you place all the traces on the top layer or you place all the traces on the bottom layer, but then in this case you use the top layer as a return reference plane or vice versa. So if one is if this layer single layer is a signal layer, then you want to have this one as a return reference plane. If this one is a signal, then you want to have this one as a return layer. Now, one of the things that you want to make sure of is when you do that, to make sure that the power ratings of these nets that you have is enough to carry the current that you have to carry. If you want to in here to feed the 50 amps of current, then you have to calculate if this polygon can carry 50 amps of current, of course. If not, you can use a larger copper pore, because you're going to eliminate one of these pores. If you have the return reference plane, you want to use all return reference plane there. Of course, you have to be careful depending on the type of voltage that you're using. So if you're using high voltage, you want to make sure that when you use this 2-layer stack up, there is enough distance for the clearance, the creepage, all these requirements, of course. So if you place the return reference plane on the bottom of these traces and in here you have high voltage, you want to make sure that the dielectric that you have is enough and it is within the requirements from the safety requirements of your board. Then one more thing that we can add in here. So these two copper planes, like we said, this is copper, so it has a certain resistance, a certain impedance. So between this point here, let's make it red, and this point here, so between these 2 points, there is a certain resistance that goes with it. So in order to, if we have a certain resistance between these 2 points, what we have if a current goes through it, if current goes through this point and has to reach this point, what I have in here is a voltage drop. Suppose this is current and this is a voltage drop that I have because I have a resistance between the 2 points. So in order to minimize that, I want to make these 2 planes equipotential. The way we do that is by adding stitching vias. So stitching vias all over. So I select a grid which is appropriate for my project. And the way you can calculate that is depending on the fastest signal that you have. So if you have a signal, a very fast signal, you want to measure what is 1/10 of the wavelength of the signal within the FR4, so not within the air, but within the FR4 or whatever material, dielectric material you are using. So you can calculate the wavelength within this material, and then you can measure what is the 1/10 of the wavelength, and you will find the distance. And this is usually plenty of it to not to create a reflection within the planes, because it can happen that in here you create a cavity. So within the plane, I can show you maybe like that. Let's say use larger distance. So what is a cavity? A cavity is, for example, this is a cavity here. So between these 2 points, there is a certain resonant frequency, which is given by this distance here. So in order to minimize this, you want to measure what is the fastest signal, then you measure what is 1/10 of the wavelength, and then you can use this as the distance for applying stitching vias. So you calculate what is this 1/10 of the wavelength. Suppose that you have 1/10 of the wavelength of the signal in the dielectric material, which is 2.5 millimeters, or higher than 2.5 millimeters. So you select the 2.5 millimeters, and then what I do is I'm going to place stitching vias for between 2.5 millimeters like that, and then I'm going to copy those. So these will connect the 2 planes, this plane with this plane, which are the return reference planes. And I can even copy this, or even Altium has already a feature that automatically does that. If not, you can just do it by hand, and you can place the stitching vias to couple these two planes together. So this signal, this plane on layer 2 and this plane on layer 3. And then you couple these by adding these stitching vias. And then what happens? Once you do that, then this plane, this point is going to have the same potential as this point. And then it happens that these two planes, they are going to be pretty much with the same potential all over. And then you're not going to have the issue that I described before, where you have a certain resistance between this point and this point. And then this means that if you have current going in this direction, then you're going to have this voltage here, which is noise, and it can couple to all the traces. But if you stitch the planes with these stitching vias, then this is not going to happen. Now, one downside of this is that if you have a larger number of stitching vias, then the manufacturer can increase the manufacturing cost of the board. So you want to make sure that you are within the manufacturing cost. You can do that by simply checking also in the capabilities page of the manufacturer, which usually they report what is the drilling cost related to it. So usually you find it under the drilling cost if you increase the drilling cost of the board. Other than that, if we have the stitching vias all over, then this is going to be good because we have, first of all, you add by adding these stitching vias, this will behave like the return vias that we were placing before when we were transitioning from signal to signal. So this is great because instead of adding these stitching vias, then we are going to have them already just by placing the stitching vias next to it. See? And this is going to already to solve many problems, because now even if you don't add the stitching vias, then the likelihood that your signal when it's transitioning is going to have a return via next to it, it's very high, and this is not going to create issues. Okay, so I hope you enjoyed this review, and I hope you find this helpful, and that is going to help to pass the EMC test on the first pass, because this is something achievable, and you just need to take care of some of the good layout techniques. Thanks for watching, and I will see you in the next one.